So in this problem, we have car rental distributions that each location is sending a certain percent of their cars to one of the other three locations in the New River Valley. And so we want to see what's happening after 3 months with the first question. So the first thing we have to do is create a stochastic matrix. So if I look at my stochastic matrix, I'm going to make my columns be Blacksburg, Christiansburg, Radford, and then the return is where is it going. So it's returning to Blacksburg, returning to Christiansburg, returning to Radford. So the percent of cars that go from Blacksburg and return to Blacksburg is 80%. So that's where my 8/10ths come from. Uh, that go from Christiansburg to Blacksburg. So if I go in Christiansburg, 7% return to Blacksburg. So the 700s in Radford. If I look in Radford, 10% return to Blacksburg. So there's my 1000s. Now do that for each of these different entries. So there's my stochastic matrix. Now the next part is figuring out how do I create the Markov chain. And so I'm going to take my stochastic matrix, and for month 1, I multiply it by the number of cars that start at each location. So that's 100 cars at each location. I multiply my two matrices and end up with 97 in Blacksburg, 106 in Christiansburg, and 97 in Radford. Now I want to go to month 2. So in month 2, I take my stochastic matrix, and now I'm going to multiply it by the solution from month 1. And now it splits up a little bit more. So I take that same idea. To get to month 3, I'm going to take my month 2 returns and multiply it by the stochastic matrix to get my month 3. And you can see that I'm getting decimals. So at some point as I go along, I do need to make just a decision to estimate when I get these rounded decimals so that they can get to whole numbers, because I can't have 92 and 99 hundredths of a car. I have to have 93 cars or 92 cars. So try to use rounding, and if need be, just try to make the best educated guess as to how it would be, as to how you should round, so that you can get your numbers to come back when possible. So here we would say that I would have about 93 cars in Blacksburg, 114 in Christiansburg, and 93 in Radford at the end of 3 months. So then the next question was, what if they were never redistributed? How many would I expect in each location over the long term? So I'm not adding cars, I'm not taking cars away from the New River Valley, and I'm allowing the distribution to occur until there's a steady state. And when that happens, what I'm really looking at is what happens if I take my stochastic matrix, subtract the identity matrix from that, and multiply it by the steady state vector to equal 0. There's my steady state. So let's actually do this. I changed to fractions because I find it easier to get to solve my equations with fractions. So here I've multiplied or changed everything over to fractions. I'm subtracting the identity matrix, and I get my new stochastic matrix I'm going to work with. So if I think about that, I have this matrix times Q equals 0. Well, to solve for Q, I need to use Gauss-Jordan elimination, or one of the other methods we've used for solving matrix equations. So got my right row being all, or my final column being all zeros, and then I'm going to use elimination, and I end up with this matrix. And what this tells me is that I have a free variable in this problem, which is going to be x3. So I know that my Q is equal to, so my first variable x1 is equal to x3, x2 is equal to 10/7 of x3, and then x3 is my free variable. So if I plug in and change this to a parametric vector, I know that if I pull out the x3, I have 1 10/7, and then for my free variable, I'll put 1. Now, dealing with it in this fraction form is kind of difficult, so what I'm going to do is I'm going to actually change this over and turn it into the probability vector, so I can actually use that to get the long-term effects for that steady state. So the first thing I do is I need to plug in some value for x3 so that I can make everything become whole numbers. In this case, I'd plug in 7 to get rid of the fraction. So now my vector is 7, 10, 7. And then the last thing I need to do is change that to the probability vector by dividing each of those numbers by the sum of the entries. And that's 30 or 24. So 7/24, 10/24, 7/24. So what that tells me is I can multiply the value that I started with for each of those. So Blacksburg I multiplied by 7/24, Christiansburg by 10/24, and Radford by 7/24. So Blacksburg will have 7/24 of the total number of cars from the original, so it's about 88 cars. Christiansburg has about 125, and Radford has about 88 cars. Now, if you look at that, you'll notice that what happens here is that both Blacksburg and Christiansburg come out at 87.5. So technically, I am listing one more car than what started in the problem. So you can either use the rounding, or you can try say that you're taking one up and one down and make a note of it as to the numbers actually round to here, but to keep it within the 300 cars, I said this one rounds down and I say this one rounds up.